In this video, we're going to look at some examples of using the root test to determine whether certain series converge or diverge. We quickly recall the root test for series. If we have a series with non-zero terms, we're going to compute the number r, which is the limit as n approaches infinity of the nth root of the absolute value of a sub n, the term of our series. If the value of r is less than 1, then our series will converge. If our limit r is greater than 1, then the series will diverge. And if the limit r is actually equal to 1, then our test is inconclusive. There are examples where this value of r will be 1 and the series will converge, and there are examples of series where the value of r will be 1 and the series will diverge. When we get r equal to 1, this is an indication that we need to use some other test to analyze our series. For our first example, let's determine whether the series from n equal 1 to infinity of 3n plus 7 over 5n plus 2 to the nth power converges or diverges. Notice that the term of our series is a rational function raised to the nth power. And whenever we have nth powers in our term, particularly when the whole term is raised to the nth power, then the root test is going to be a very useful test, as it will allow us to get rid of that power. So here, we're going to let r be the limit as n approaches infinity of the nth root of this expression, 3n plus 7 over 5n plus 2 to the nth power. Notice that we're leaving off the absolute value bars here, because when n is positive, like it is in a series, 3n plus 7 is positive, and 5n plus 2 will be positive, and so the quotient of two positive numbers will always result in a positive number. And so here we have the nth root of an nth power, and so our nth root and n, the power, will cancel out completely. And what we're left with here is the limit as n goes to infinity of simply 3n plus 7 over 5n plus 2. So we have the limit here of a rational function, 3n plus 7 over 5n plus 2. To compute this limit, we could multiply the numerator and denominator by 1 over n, or we could also use Lupital's rule here. It's also a very straightforward computation. Here, as n goes to infinity, we're going to get an infinity over infinity indeterminate form. And so we're going to apply Lupital's rule to this expression. And the derivatives are here very easy to do. The derivative of 3n plus 7 is 3, and the derivative of 5n plus 2 is 5. And so here we get a limit of 3/5, which is less than 1. And so here our value of r, the limit as n approaches infinity of the nth root of our nth term, is 3/5, which is less than 1. And therefore, this series converges by the root test. In our next example, we want to determine whether the series from n equal 2 to infinity of n to the nth power divided by natural log of n to the nth power converges or diverges. Notice the series starts at 2 to avoid dividing by 0, which would happen if n happened to equal 1. We notice that the term for our series involves the nth powers of different expressions, and so this indicates that the root test would be a useful strategy to try. So we're going to compute this number r, which will be the limit as n approaches infinity of the nth root of n to the nth power over the natural log of n to the nth power. And here, because everything is raised to the nth power in our series term, the nth root will cancel with both of our exponents of n, and this leaves us to compute the limit as n goes to infinity of n over the natural log of n. So we now want to compute this limit. If we evaluate numerator and denominator separately, we see that we do get an infinity over infinity indeterminate form. And so we can apply L'Hopital's rule to this particular limit. And when we do that, we see that we get this equal to the limit as n approaches infinity of the derivative of n, which is 1, over the derivative of natural log of n, which is 1 over n. And simplifying that expression, we get a very simple limit, the limit as n goes to infinity of n. And so here this will be a limit that diverges to infinity, and this limit is certainly greater than 1. And so here we have a series where the limit of the nth root of our term is greater than 1, and therefore we conclude that our series will diverge by the root test. If you'd like to try a couple similar problems on your own, you can pause the video and determine whether the following series converge or diverge. First, we have the series from n equal 1 to infinity of negative 1 to the n over n to the n. And second, we have the series from n equal 1 to infinity of the quantity 12n squared minus 3 divided by 4 plus 11n squared, all raised to the nth power. You can resume the video and see full solutions for these two series in just a few seconds. For our first series, we want to compute r, which is the limit as n approaches infinity, of the nth root of the absolute value of negative 1 to the n over n to the n. Notice that because of the negative 1 to the n in the numerator, we do need to compute the absolute value here, so that when we take the nth root of our expression, this expression is actually defined. When we take the absolute value, we simply remove the alternating sign in the numerator, and we're left with the limit of the nth root of 1 over n to the n, which is easily seen to be the limit as n approaches infinity of 1 over n. This limit is evaluated to be 0, which is less than 1, and therefore our series converges by the root test. And for the second example, we take the limit as n approaches infinity of the nth root of our term. Because our term is an expression to the nth power, the nth root and nth power cancel out, and we're left with the limit as n approaches infinity of 12n squared minus 3 over 4 plus 11n squared. Because n squared is the largest power of n in the denominator, we multiply the numerator and denominator both by 1 over n squared. When we simplify this and evaluate our limit, we get a value of 12/11ths, which is bigger than 1. Since we have the limit of the nth root of our nth term equaling a number greater than 1, this series diverges by the root test.